Okay, so on the lab, here's the first thing that hopefully you have is your force, your elongation. Now, certain labs or graphs you know are going to start at 0, 0. So why is this graph you know is going to start at 0, 0?
Because
There's no force. There's no.
Yeah, if there's no force, guess what? You don't have any elongation, okay? You absolutely know that's going to be a point. So you got these other points, boom, come in here with a ruler, as Cohen said, draw the line of best fit, okay? If it happens to go through some data points, great. If it doesn't, hey, welcome to science. But here's going to be one of the most critical things. So you're going to go to that elongation. So like, well, what was your elongation on that 1.5 kilograms?
Wait. 0.179 meters.
0.179. Okay? So this is what I'm going to look for on Will's data. Okay? So that little asterisk, bottom right corner of this data table, right here. Okay? So there's that asterisk. I'm going to look at Will's, and that's going to be 0.179. So then Will should go to 0.179 and draw a line straight up until it intersects the line of best fit. Okay? Then over here, Will is going to write, 0.179 meters, and whatever the value of that force that is that corresponds with the line of best fit. Now, if that happens to be 14.7 newtons, which is the actual force, hey, great, you got lucky. Happens about 10% of the time. Most of the time, the line of best fit does not correlate with that particular value. Okay? So that's what's going to be out here. So that's one of the things I'm going to look for. On your graph, did you put 0.179 and, or whatever your data is, and whatever that corresponding value force is from the line of best fit? Okay? Because you're going to need that later on. At some point, you need to calculate the slope.
Adjusted for
Okay?
what it should have been.
You need to pick some points. If you want to pick that as, if Will wants to use that as one of his points, hey, great. Will can use that as one of his points. But you got to have 2 points to find the slope of the line. And again, everybody's slopes are different. So the only thing I can grade you on is the process. So either on the graph or in that space below number 2, I want to see how you found the slope of the line. Okay? Typically, these spring constants, and this is a huge ish, they're typically around 80 newtons per meter.
Nice.
Okay?
What'd you get?
49.
Oh.
Yeah, 53.
Yeah, we all got like 50.
Okay, well, like I
okay.
said, that's, you guys might have just had
A weird
a
spring.
weird spring.
Yeah, your spring sucks.
So, what did you guys get?
82. I got
To be
85.
fair, ours almost went like off.
Yeah, it was like at the very bottom.
Yeah, it was very.
But that's just because you started with a long spring.
It was very springy spring.
No, it's not a very springy.
No,
very
well-
springy spring. It's
No, I mean like as it has the essential qualities of a spring. No.
Okay, well, that's why they call it a spring. Okay.
very springy spring.
On
Spring
page
is
2, kind of about 2/3 of the way down for trial 1,
It's
I want to see the
I
calculations
did this.
for us 1, us 2, delta us, and UG. And when I say calculations, I don't mean just writing down 1/2 k x1 squared. That is not showing calculations. That is saying, oh, I can copy down a formula. This doesn't tell me that you plugged in the right numbers. Okay? So typically, and this is an ish, typically your us1, that smaller distance, is typically around 0.4 to 0.5. The second one is around 1.5. Okay? Your delta S is typically around 1, and hopefully your UG value is also around 1. Okay?
What'd you get?
Now, that's a huge ish depending upon your spring constant, how much you made it oscillate, all of this stuff.
Maximum amount of oscillation.
So that's an ish. Now, here's the bigger idea, is that when you compare the change in us to UGG, hopefully those values are pretty close together, okay? In an ideal world, they would be the exact same because all you're changing is one type of energy for another. So as that stretches, you're storing more us, but you're losing gravitational potential energy. So in an ideal world, the delta S and the UGG values would be identical because you're just changing forms. Okay. On number 6 on page 3, this is why you need this value. So when you're finding this area here, if I'm Will, I'm going to use 0.179 and whatever that height is based.
I panicked. I was gonna be fine. The table would have caught me, but I panicked.
I don't want the table to catch you. I'm also on this table.
No. The table
Back behind.
catches.
This table or the table back behind would have caught.
This table.
Well, the table behind's gonna like catch your neck and
Yeah, the table behind would have caught my head on the way
and
down.
created torque and
Yeah.
bad things would have happened.
and then Preston.
So you
Preston
keep
works
this
there,
in mind when we're
yeah.
talking about center of mass today. Okay? That little deal right there. Okay?
Okay.
All right.
Cohen falls out of his chair.
When you get to the question about, on number 11 on that multiple choice question, and again, don't flip out and go, oh my God, it's just variables. Well, you're looking for power, okay? And you keep this in mind, especially for this class. So power is either going to be work divided by time, and in the second semester especially, we're going to look at that as just change in energy per unit of time. Okay? So that's going to be a big idea. So number 11, you're talking about changing the kinetic energy. Well, how do you calculate kinetic energy? 1/2 mv squared over time. Okay? Then it's just a matter of trying to do the manipulation to fix that. Now, in contrast to that, when you get to number 12, since power equals work divided by time, you can write that as force times distance over time. And distance over time is the same as velocity. Okay? So that might be something that you can work with, certainly the distance over time part on number 12.
Yeah, 'cause it's-
When you get to the question with the glider, and that one where you have to have that as a fraction, so here's the deal. So it has a certain amount of energy, 1/2 mve squared, okay? Just before it hits the bumper at the end of the track, the glider bounces back from the bumper with a velocity of v/4, the energy converted to heat in the collision. So if you want to, if this is flipping you out, so this is how much energy it's going to have when it comes in, it's going to bounce back with E equals 1/2 m, but then what are you going to do for the velocity?
1/4 v squared.
Yeah, so it's going to be v/4 squared, okay? So what you want to look at is not so much how much energy that it has when it leaves, but it's talking about how much energy are you going to lose in the collision, okay? So obviously there's a 4 squared in there, so which leads you to the idea that something might involve
16.
16, okay? Just because by virtue of the fact that you have that. Now, when you get to that last question with the spring, and that's oscillating,
I just guessed.
just keep in mind that force equals kx, right? Okay, force equals kx. So the bigger x is, the more
Force.
force there's going to be. The more force there's going to be, the bigger the acceleration is going to be. Okay? So just keep that in mind. So-
Is there more than one correct answer on that?
No,
The other ones just don't make sense.
no. On all of these, there was only one correct answer.
Move your hand.
And let me give you a hint. None of your answers on the 4 multiple choice questions should be the same. There
Yeah.
should be 4 different answers.
Oh wait, process of
one of these is
Neat.
Yeah. If you just
One of
do
these is
confirmation
wrong.
process.
Wait.
Will, darn,
Stick with
what
the
of
bladder
these
one.
is
It's the
wrong?
bladder
Oh,
one.
there's the
Just
head
the bladder.
scratcher,
It's the
because then you
bladder
don't know
one.
which one it is.
Mm-hmm.
I know it's not D, that has
I
a
said
4.
B.
Oh,
B.
B? It's
Is
not
it a
B, that has
vowel?
4 as well.
All right,
Oh,
anything
is
else
that
on the
'cause
Four
lab?
squares.
Is it
Going
this one?
once,
Because when it
going
comes to here, it's
twice.
negative.
Sold. Staple the
Okay.
graph to the back
I'll just go with that. I'll
Wait,
trust
I
you,
didn't-
Cohen.
Oh, wait,
and
Bold.
stop yonder camera.
Yes, it is
Okay.
bold.
Can I see
Very
your
bold
graph?
of you.